Nice little question that we're just going to go through from last week. And it reads, a skier skis down a frictionless, snow-covered slope that forms an angle of 25 degrees to the horizontal. He starts skiing from from point P, 20 meters above the ground. At point Q. At the bottom of the slope, he hits a rough horizontal surface and experiences an opposing frictional force of 300 newtons. The total mass of the skier and the skis is 60 kilograms. Number 1, calculate the net work done on the skier while he moves down the slope. We'll end there. Okay, we'll just do number 1, then we'll progress to number 2, and then we'll progress to number 3, and then we will progress with the content and progress with another exercise. Okay, so for the purposes of this time now, let's just focus on answering question 1. There is the drawing at the bottom there. I think you guys can see the drawing and the question there as well. So just question 1, please, and we shall therefore go through it after. The first obvious approach to this question for number 1, okay, step is always to maybe draw a free body. Okay, always start drawing a free body diagram. Okay, and I always recommend this because it just helps. Okay, if you know how to use it properly and know how to use the effects of it properly, it just helps with answering questions like these. Okay, first thing to note is maybe you even want to draw a slope. Okay, so we're just focusing for question 1 on just the slope. So here's my free body. Okay, we draw that a little closer to the free body diagram. Okay, obviously I know that going straight down here is FG. Okay, going this way I know is obviously FG perpendicular, and I know going this way I know is obviously FG parallel, so I'll draw that up here. Going this way is FG parallel. Okay, so FG parallel is going in the same direction of motion as the skier. Okay, also we know that the delta x, the displacement or the distance, is also going this way. Now that I have my diagram, I can see that I could use this method or use FG parallel and the slope of the length. I mean, this is the length of the slope, sorry, not slope of the length. Sorry about that. Okay, so of course I know that there's an angle of 25 degrees to the horizontal, so I know that is the same angle up here. So I'm obviously, for calculating FG parallel, I know that's going to be equal to still mass times gravity and sine theta. Okay, nothing new, or should be nothing new. Okay, because that's equal to that. Okay, I'm welcome to go ahead and put that in my calculator and solve. So I'm welcome to solve for FG parallel if I want to, which in this case I will. They told me the mass of the ski and the skier is 60 kilograms. Gravity stays 9,8 times sine theta. In this case was sine 25 degrees. All right. Here we go. 60 times 9.8 times sine 25 gives me an answer of, let me see, 248,499. So I'm going to round that up to 248,50 newtons. Okay, because it's F, force, newtons. Great. Now W net is only equal to the work done by the force of gravity, or force of gravity parallel. In this case, we're using the parallel component of the force of gravity. Okay, and that is equal to obviously FG parallel delta x cos theta. I already worked out this bad boy over here, so that is just equal to 248,50, same thing, multiplied by the distance, which was equal to, did they mention that? Just check. just have a look here. He starts skiing from rest, 20 meters above ground. All right, let's just check what 27 meters above ground. So let's just have a look here for how am I going to calculate delta x. Give me. All right, so the way we calculate delta x in this case, because obviously we're not sure, the drawing showed that his height was 20 meters above ground. Okay, because we know we have this little triangle, if I draw this little triangle out for you guys to large scale it, see. Okay. Okay. Remember, so this triangle is this triangle. Okay. So I'm drawing. So this is the slope of the snow-covered slope. The skier is going to ski down. So I'm actually drawing this part here, and so I have 25 over here. This part here was 20 meters. Okay. So the height, okay, was 20 meters. This is point P, and this is point Q. Now PQ is my hypotenuse. Obviously, I am looking for opposite over hypotenuse is equal to sine 25 degrees. So 20, this part over here is obviously my delta x, divided by, I can't actually draw a straight line, by delta x in this case, which is my hypotenuse, is equal to sine 25 degrees. Okay, obviously to rearrange that, delta x is going to equal 20 sine 25 degrees. Okay, if I take 20 times sine 25 degrees, did I do that correct? No, sorry, not 20 sine times sine 25, it's divided by sine 25. Divided by sine 25. And if I do that, I'll get my delta x to equal about 47,32 meters. Okay, so delta x in this case is now going to be 47,32, so it's multiplied by 47,32. FG parallel is going in the same direction as the skier, or as delta x, because they are both moving this way down the slope. So my theta is, there's no angle formed. They're both going the same direction, cos 0 degrees, which is equal to 1. And my final answer is therefore equal to 11,760 joules. Okay, this is the part where I take questions.
Why is your cos theta 0 and not 180?
So cos theta is 0 in this case because we never used frictional force.
Okay.
So
when you don't use friction, then cos is 0.
Okay, so let me just correct your definition slightly so that you don't get confused in the future, is that when the force is in the same direction as your displacement, you see they're both going down the slope. Okay, if something is doing that, they parallel to each other. That means no angle is formed.
Okay.
No angle. So when no angle is formed, it's cos 0. That's what that 0 means. I mean, there's no angle formed by the force and the direction of the displacement. In the same direction. Opposing this force over here is obviously frictional force. All right. But this surface here is frictionless. So there's no friction between P and Q. So in other words, if friction was going that way and displacement is going this way, then indeed the angle formed would be 180 degrees.
Okay.
Cool. Any further questions?
JP,
Talk to me.
what two components do you use? Friction and?
No. I'm confused. Would you say which two components are you talking about when you mention friction? Are you talking about the angle that forms with friction?
Yeah, like we use cos 0 and cos 180.
Okay. Um, give me one sec. Okay. So cos 0 degrees. Okay, this is where the force is in the same direction as delta x. Okay. When you have cos 180 degrees, okay, that's when your force is in opposite direction as delta x, which in this case would be friction. All right. Okay, great. That was a nice little question there. All right. Okay, so what we're gonna do, and that was probably the easiest way to approach it. All the other methods are just too confusing. I'll send those to you guys via the WhatsApp group. The other methods, you can just have a look at them, but that's by far the simplest method for to use for solving this question. Okay, let's go back to the question. Okay, we're gonna do question 2 now. So obviously we kept our initial question there, or not initial question there, but our initial answer for number 1, because it probably is going to come back. They now ask us to calculate the speed of the skier at point Q, which is at the bottom of the slope. All right, so let's go ahead and do that question. Again, there are 2 ways to do this, but obviously now when we're looking at calculating speed, we know that as the skier is moving down, he must have some form of kinetic energy. Okay. Also, we know the speed at which he started from. Why or how do I know this? It says he starts skiing from rest. Now again, I must say this again because again, I get this question of what was the initial speed or what was initial velocity. From rest means he's not doing jack. He's doing nothing. All right, and nothing in number form or in number language is 0. Okay, so he starts skiing from rest. So I'm going to let you guys do this question on your own, but what I'll do is I'll set it up for you guys. What we're going to need to approach this question is saying, well, I just calculated, let me start from all the top up here. I just calculated W net. I just calculated that. I have W net. And I know the work energy theorem formula is equal to W net is equal to the change in EK, which is equal to EK initial, or EK final, sorry, minus EK initial, which is further equal to half mVF squared minus half mVI squared. Okay, so this is what you're working with, lads. All right, let's see what question you come up with, or what answer you guys come up with in the next 3 minutes on the hour of 6:01, or 6 o'clock, rather. No, actually 6:01. All right, guys. So you guys got the setup for the question, and using this method is a very quick way of solving. So I'm just going to write down in another color quickly about the information that I do know about how to solve for VF. Is that my VI, just in this equation alone, is equal to 0 meters per second because he started from rest. I do have mass because it was given to me and of 60 kilograms. Didn't have to work that out. My W net that I was given in this case, all right, was given to me by 11,760 joules. and I'm looking for VF. Okay, we go back to light blue. Okay, so let's just work from here quickly. I'm going to bring this part over here. So, good thing to notice, maybe to simplify this, because I know that's 0, half mvf all squared minus half mv, not v, half m. I know vi, the value of vi was 0, which simplifies it to just half mvf squared, of course. Now I can, a simplified one will be obviously w net is equal to half mvf squared. Now I can just sub in my values. So w net is 11,760, which I calculated in my previous question, equals to half mass 60 vf all squared. Okay. Obviously, I know that value. All right. I have 11,760 is equal to 30 vf squared. What I need to do to get vf on its own, I need to divide by 30. What I do to the one side, I must do to the other. Okay, that 30 and 30 cancel. All right, vf squared is going to equal, I'm just going to perform that sum quickly, 392. And I'm going to square root both sides. Therefore, the final velocity of the skier when he gets to the bottom of the slope, which is point Q, is equal to, anybody have an answer? Be polite and ask.
I didn't.
I
I
got
done that,
9.
but yeah, same. But I didn't know you must round the W net of the whole number. Mine's a decimal form.
That's perfectly fine. There is decimal leeway.
Oh yeah, so I also got 19.
Good. Okay. Well, because I did the whole number, mine will have 19 point something. So if you got the 19 meters per second, you are correct. But if I use this value, I've got 19,7989, which rounds up to 19.8
80.
or 8
Yeah,
8 or
same.
80
Also got
meters per second.
Yep.
yeah.
Okay, yeah. Let's put
Yeah, I got that.
you put
Yeah.
90.80 for Christian. Okay, lovely, beautiful. You obviously know what that means. Celebration time! Yay! Excellent. Right now, congratulations to everybody who got it right. The third question and final question for this little exercise. So let's just go back to the question. This one's not too bad. This one is, now calculate the horizontal distance covered by the skier before he comes to a rest at point R. So you can see over here at point R, this little, and obviously this is now the rough surface. So it's no longer the smooth slope anymore. It's a little rough patch here. So QR is, we are looking for that distance. So we need to calculate that distance. Okay. I'm interested to see how you guys approach this question, and I am interested to see the answers as well that we get. So I will allow some time for this question. This one does involve quite a bit of work, so I'll give about until about quarter past. Let's go ahead and let's approach this question. Okay, so the third question here was, calculate the horizontal distance covered by the skier before he comes to a rest at point R. Right, so we're calculating the distance of QR, as we see over here that I've kind of just separated for you guys into two separate drawings. Just to read again from the other points in the scenario, to remind you guys, he says, or the quick question says rather, at point Q at the bottom of the slope, he hits a rough horizontal surface and experiences an opposing frictional force of 3 300 newtons. So that means that the frictional force over this period of this surface across this distance, which is unknown, is 300 newtons. So here's where our free body diagram comes into play. All right, I'm not going to draw the distance of the surface, but obviously you can see from point Q to point R, it's going that way. This is my delta X. And he experiences an opposing frictional force. Now the distance, or the delta X, is in that direction. In other words, he's going from point Q to point R. Friction is going in the opposite direction, which is that way. This forms an angle theta of 180 degrees. Okay. So now, important thing that what I've denoted here is that over this point Q to point R, the only force that is active here is my friction. So the net force comprises of only one force, which is the frictional force, which is equal to 300 newtons. So I can, and also it's the same network that is applied here. That or same formula rather. So if F net only comprises of the frictional force, right? And also the net force, or the net work rather, is equal to the change in EK. That's the formula. Remember, another way of calculating net work is to use the net force. If I use the net force in my W net formula, I'll have an equation called F net delta X cos theta is equal to the change in EK. Pretty sick. All right, now I can begin by substituting in, try and solving this equation. This part here is a little easy because that is that. So let's just go and sub in. Therefore, 300 multiplied by delta X, which is unknown, multiplied by cos theta, and theta in this case is 180 degrees. Because of this drawing, explains it all. Equals to the change in EK, which we know that the final is 0. So if we sub in here, we have half of 60 times 0 squared minus half of 60 times 19,80, or 19.8, same thing, all squared. Right, if we simplify a little bit, just a little bit, not going to simplify entirely, but we'll have 300 delta X, all right, times -1, because cos 180 is equal to -1. It's going to equal -30 times 19,80 all squared. And I can solve for that actually. Let me actually just erase all this. And just give you that value. Rather, it's to just save up space and time. So I have half 60, which is 30, multiplied by 19.80 all squared, or 19.80 squared. Get an answer of, let me just maybe take the 0 away, see what I get. times 90.80 squared, so I'm just going to get a, it's weird. Weird. So guys, my calculator is just doing funny stuff. All right, I got it to work. So that's going to be minus, 11,760. Sorry. Okay, basically it was just the previous, the W net that we got in the previous question, actually in question 1. Basically that's what it is. Okay, it seems that that is the same value. If you got, for example, 11,761, all right, because you just put 90.80 squared immediately into there, that is perfectly legit. Okay, it's still the same thing. Doesn't matter. There is obviously leeway for decimals, etc., etc. Okay, I just use the full decimal number. It's perfectly fine. So this will give me simplified negative 300 delta x, and that's going to give me, obviously that stays the same, minus 11,760. Divide both sides by minus 300. That was shockingly awful. Okay, here we go. Minus 300. They cancel by minus 300. I'm going to go up to the top here. Therefore, delta x in this case should give us an answer of 39.2 meters. If you didn't say delta x, you could have also said, therefore, QR is equal to 39.2 meters. Okay. Anybody get that? Anything? Anybody unsure of anything?
JP,
Hello?
I got the same answer note, but it's just negative. And I used a different
Yeah, same.
method.
I also got a negative one.
Okay, maybe you guys want to talk to me? Yeah, okay, start with
Okay,
you
you
first.
go. Okay. I used W net
Yes.
equal to F net delta x cos theta, no?
Okay, so you use that. Okay, great.
And then I subbed it in, and then I had to divide by 300 the 11760, and then I got a negative answer. Negative
So you
9.2.
okay, so you divided it by positive 300.
No, negative.
So this was a negative. This was positive
Yeah.
11,076. Okay. Do you understand why that is incorrect though?
No.
Okay, cool. So this change in EK, obviously we know to be equal to half mVF squared minus half mVI squared. Correct?
Mhm.
Okay. At point R, like I said, VF is equal to 0 meters per second. At point Q, velocity is equal to 19.80 meters per second. So this becomes our VI. So if VF is equal to 0, it becomes 0 minus all of this, which gives us minus 11,760.
Ew. Okay, I
Does that-
understand.
Okay. I'll leave that out for you guys over there if you guys missed this part over here. Maybe you guys are, maybe that's not on your screen. Christian, do you also get it now, or do you see where you made your mistake?
Mm-hmm.
Cool.
Understand.
Hello?
Can I at least just send you a picture of what I did?
Yes, please do. I'd love to see. Before we move on. All right. In our final hour of 30 minutes, or hours, all right, or minutes rather, we are going to be focusing on two things. Okay? We're going to be focusing on what do we mean when we talk about conservative, okay, versus a non-conservative force. Okay. When we're doing work energy theorem and when we're doing work, we classify forces into these two categories. Okay. Cool. So let's first start by obviously defining what these two are. So for conservative, and I must say conservative force, just now you think I'm defining the word conservative. conservative force, all right, first of all, it is a force. Duh. Okay. It is a force for which the work done in moving an object in moving an object between two points, is, and this is a big word here, independent. It is independent of the path taken. In other words, delta x does not mean anything to this force. Conservative force is a force for which the work done in moving an object between 2 points is independent of the path taken. Okay, that's conservative. Obviously, we can therefore form a definition for obviously the second one, which is a non-conservative. Non-conservative force. Okay, first of all, it is a force for which, okay, it's a force for which the work done in moving the object, B, object between 2 points depends or is dependent on the path taken. So the path taken plays a big role. Delta x means something to this force. Okay, so let's figure out how we can distinguish between these by possibly drawing up or setting up ourselves a little table. Okay, the table method will definitely help us classify and help us distinguish better between these two forces. Okay, I'll take up the entire space here. Here we go. And here we go. This one I'm going to use conservative forces and give examples of each. And this one I'll be using non-conservative forces. Not sure why it does that. Right. First point. Non-conservative forces. All right. Couple will be gravitational force. All right. Electrostatic force. We don't need to be too concerned about. Static force. And also the elastic force in a spring. And for non-conservative force, these we know very well because we've been dealing with them all the time. Force applied or applied force, okay, is a non-conservative force. All right, and applied force can be a pulling, pushing, or motor drive force. Okay, all of those are applied forces. All right, the frictional force, as well as force of tension, okay, which we probably haven't seen for a while. The force of tension. So again, we've classified what conservative forces are and what are non-conservative forces. Okay, we have names for each. Okay, so if you want to have a look, for example, at the work done by a gravitational force, okay, now gravitational force, in other words, that does not depend on the path taken. So in other words, the force of gravity does not depend on the path followed from the starting point to the finishing point. Okay. If we have Fg over here, okay, we want to have a look at that. First of all, we know that is independent of starting points, or from starting to finishing points. Finishing. Okay. For example, if I have a little curly little frictional thing here, let me draw it a bit lower. There we go. Add a little box. All right, going in this direction. In other words, it starts from here. Sorry, this is its initial part here, and it ends over there, and it has a height of h, a certain height. Okay, which you won't know, which you don't know yet. Okay. In other words, over here, the work done by the gravitational force is only concerned just because the path was from I to F this way, gravity is still going in the same direction as H. So the work done here by the force of gravity, in this case, all right, is equal to the change in EP. Okay, the change in EP. Okay, or actually, should I say the negative change in EP for this one, because this is the difference between the final and initial energy values. Okay, in other words, we are taking into account that the reason why it's negative, okay, it's going this direction and gravity is going in, and obviously gravity is going this way. Gravity, the force of gravity is always going downwards, okay? And so it ends up being negative to the negative change in EP, which is equal to obviously minus EPF minus EPI, okay? Minus times a minus, which gives you a positive, which will basically just give you EP, or the initial potential energy, minus the final, and therefore this is conserved. How many times would you get this in the exam? Almost never. This one is probably the most focused on, okay? And I'll show you why. Obviously, we know this one. In other words, if you must use the force, let's use FT, the tensional force, or the force of tension, which we haven't looked at in a long time. Obviously, this is dependent on the path taken. So from start till finishing point, if I had a slope, okay, this was the initial point, and FT was in this direction, and it ended up over here. My final point, from this point to this point here, would have obviously been delta X. Okay, this point over here, this is not equal to the difference between final and initial values. Okay, it's not equal to final minus initial values. Okay, put X there for to replace whatever variable. Okay, also this is not conserved, okay, because energy is lost. Energy is lost in these non-conservative forces, and it's lost to a number of things such as either heat or sound. Okay, and I'll show you why in the next couple of moments, because even though we've classified these two things, there is a formula for the work done by non-conservative force. But before we get there, I need to just stop off at a pit stop here and explain the conservation of mechanical energy. So if we have a look at the conservation of mechanical energy, which back in the day where I was at school, we used EMEC. But I see in most textbooks of today, it's used as capital M, capital E for ME. Okay, the conservation of mechanical energy, obviously we know that when everything is conserved, it's done in an isolated system. Okay, with that being said, there is a principle for this. Okay, so the principle of the conservation of mechanical energy, or the conservation of energy, okay, is that in an isolated system, all right, in an isolated system, the total mechanical energy, all right, total mechanical energy, which is obviously our gravitational potential plus our kinetic energy, remains constant. All right, so with an object, this pertains to objects such when object is in free fall. All right, we obviously remember from VPM, if an object is in free fall, if an object is on a slope, all right, slope similar to that would be if it's in a pendulum, so it swings from one point, or a roller coaster, example. All right, mechanical energy would be used here. Okay, so the formula for that would be ME, mechanical energy at point A, is also equal to mechanical energy at point B, all right, or between 2 points. If it's on a slope where you have top and bottom, obviously, you would say, well, ME at the top is obviously equal to ME, or mechanical energy, at the bottom. Okay, because it must be conserved. So if anything is conserved, it's in an isolated system, it should all be the same. If you have 3 points, let's say you have A, B, and C, then it must also be equal to mechanical energy at point C. So all the same. Okay, but normally in a pendulum, most of the time, most of your pendulums will only ask you between 2 points. All right, or if there are more than 1 point, they'll probably break it up. They'll probably break the question up. They'll start, okay, between these 2 points, what's the mechanical energy? And between these 2 points, what are the mechanical energy? Then they'll give you maybe a third question, might say, okay, therefore, what is the total mechanical energy in this scenario? Obviously, you just add the 2. All right. So now that we've introduced mechanical energy, which is the concept of, if I simplify this, mechanical energy would be, let me just break this up into maybe simpler, smaller chunks. EP plus EK, still all at the top, is equal to EP plus EK at the bottom, which means if I'm going to simplify, mgh plus the kinetic energy, which is half mv squared, is equal to also mgh plus half mv squared. Okay. Obviously, depending if it's on a pendulum, where they've given you the top part or they've given you the bottom, you'd obviously just use the words that pertains to the scenario. If it's on a slope, but usually whatever you start with, whatever the top, if it swings from the bottom, it swings to the top, then whatever's at the bottom must equal to what's at the top. Or if it swings from the top down, whatever's at the top must be equal to the bottom. And this is how you would set up your question. Okay, and then you just sub in for your normal values. Now, obviously we can see, all right, that mechanical energy comprises of potential energy and kinetic energy. Okay. Now, when we are looking for the work energy theorem question and how to define what is the formula for work energy theorem as well as a non-conservative force, because we know that the work is done by a lot of non-conservative forces we mentioned in the previous page, which was applied force, force of tension, and frictional force. So if you want to have a look here just on the side of what is the formula for if I don't have the value, or I'm not told what type of force is it, I'm just told it's a non-conservative force. formula to that for a non-conservative force, so the work done by a non-conservative force, by the way, is denoted as WNC. NC is non-conservative. Okay? That is equal to the change in its object's kinetic energy plus the change in the object's potential energy. Sometimes it is not noted by non-conservative force. It is also given by the work done by external force. W external is equal to the same thing. An external force is a non-conservative force. All right. So, any questions? I'd like to show you an example. All right, no questions. So maybe I can just show you guys an example to maybe make this all clear, or a bit clearer, should I say. Remember I gave you a scenario in last week's question about Susan, and she rides a bicycle. The mass that was given to in this equation was 60 kilograms. Delta X is equal to 8 meters. Or some frictional force that was in that scenario was 30 newtons. The initial velocity that she was riding at was 10 meters per second. It also was a constant speed, and we found that VF was equal to 8,08 meters per second. This was at the top of the slope, but we are allowed. And did I say frictional force? So frictional force was not 30, it was 20. Sorry, I just read the scenario properly now. So now that being said, we can use the W in C is equal to the change in EK plus the change in EP formula, because the non-conservative force over here was friction. So we can calculate the work done by friction. So the work done by friction's formula obviously is given by the frictional force, delta X cos 180 degrees, is equal to, well, we know the change in EK. We have to obviously expand this now, which is half mVF squared minus half mVI squared, close bracket, plus we know which is change in EP or potential energy, which is mgh final minus mgh initial. Okay, I've expanded. I know where I'm going. My frictional force was given by 20, so I'm going to sub in 20 for force of friction. Delta X was 8 meters. Don't need to write meters in. Times 8 times cos 180, that stays the same, or I can just substitute that as times -1, because that's what it is. All right, equals, oh, part that I didn't, HI, the initial height was 0 because she started at the bottom of the slope, and then she got to a height of 1.5 meters at the top of the slope. And yes, so I'm just showing you guys basically how to get to this answer using this method. All right, so again, half of 60. VF squared is what I'm looking for, minus half m times 10 squared, brackets, plus mgh, which was 60, so that should also be 60, but it's the same thing. 60 times 9,8 times 1,5. We use a square bracket here just to don't get confused. Minus square bracket 60 times 9.8 times HI. The value for HI was 0 meters times 0. So I know that's all going to be equal to 0 eventually. Okay. 20 times 8 is 160 times -1. I know is negative 160 equals to 30 VF squared. all right, minus 3,000, right? Because half of 60 times 100 is 3,000, because half of 60 is 30, times 100 is 3,000. I don't need to explain that, of course. I'm going to keep the brackets around this one, because that's 1 0, so I just obviously put down this value, plus 882. Okay. Obviously, I want to get 30 VF on its own, so on this side, I'm going to have minus 160 minus 3,000, plus 3,000, sorry. There's a minus over there, and minus 882. It's going to give me 30 VF squared. So punch that in on my calculator. So I'll solve for the first part there, which is 3,000 or plus or minus 163 plus 3,000 minus 882, which gives me 1,958. Gives me 30 VF squared. Divide both sides by 30. Okay, and then we're going to square root this as well to get VF on its own. Therefore, VF should equal to exactly the same answer that we got previously last week, 8,08 meters per second. Okay, so this, by using this method, I've also checked that the way we did it last week with just using work energy theorem principles, that way we have to use W net. So we had to look at the force of gravity parallel plus the work done by the force of friction equals the change in EK to get the same answer. This one we used work done by friction, which is the non-conservative force, equals to the change in the object's kinetic energy plus the change in the object's potential energy, and we got the exact same answer. All right, this is in a closed system, obviously, so there's no external forces. Are there any questions maybe pertaining to this example that I can help you guys feel better about? Any questions? Everybody understand? Thanks, guys. We are done for this evening session.